parallel circuit.
Action.
You said action and printer start working. I'm not sure what's going on, but it was quite a coincidence there. Now, these things, you have to, it doesn't make sense unless you put something in there. So I'm going to go ahead and put x of c as 3k. X of L, 9k. And R,
Oh.
That's what I'm buying for the rest of the
soda,
class.
huh? That's soda? Yeah, he'll do that
Soda.
too. So they'll do that, yeah. Yeah, bring back the money.
and let's say I'm having
Which car?
180 volts. That's quite a bit, man. Just for the heck of it. So this is not all real anyway, it's just a theoretical. Okay, that's going to happen. Obviously, I'm going to have a current flowing in there. Let's say C now. I'm going to have a current through R, current through L. And I go like this, so you know it's AC current. IC, IL, IR, IT. Now to solve this problem, the way approach I will take is, right away I go to the phasor diagram. Phasor, to me, is the key to understanding RLC parallel impedances. To me, phasor is everything. So right away I'll have to just draw the phasor and then look at it. A lot of things actually begin to visualize when you do that. So I'm looking at I sub c. If you remember, I sub c is now going upward, isn't it? Now before I do that, let's go ahead and find out what these are. I sub r is going to be V over R, 180 over 10K, that's 18 milliamps, isn't it?
Yeah.
I sub L is equal to V over X sub L, 180 over 9K is equal to
20 million.
20 milliamp. And I sub C equals to V over X sub C, which is 180 over 3K. And that is equal to
60.
60?
Yeah, 60 million.
60 milliamp. Okay, now I like to just draw this picture here and to get the feeling for this. So IC is going to fall into the first quadrant up there. So I'm just going to draw, this is 10, so this is 10, 20, 30, 40, 50, 60. So here is where you want I sub C. I sub R is 18. That's 1, that's 2. Later on here, I'm going to say that is my I sub R. And I sub L falls below. 1, there's 2. Right there. I sub L. You see this? So look, right away I'm looking at this and I say, the capacitor is dominating. And if I'm looking at it, I can see that IC is 60 rather. X of C is 3K. 3K is the lowest impedance, or should I say reactance, in all three of these devices. So it's going to draw the most current. It's going to dominate the circuit. And I can see it from this phasor. This almost looks capacitive because the end result. So end result of these two is going to be, I'm going to call it I sub x. So I'm subtracting I sub c from I sub l, and I'm coming up with 1, 2, 3, 4. And this would be my I sub x.
That'd be 2. Oh, no. No. Okay, yeah, you're right.
So I'm saying that I sub x then is going to be equal to simply IC minus IL, which is 60 milli
40 milli.
minus
20.
20 milli,
Yeah.
which is 40 milliamps. And that's what, how much that is, 40 milliamps. Now I draw the phasor, and this is going to be my total, I total right there. IT, and here's the phase angle right there. So I'm going to say that I total then is equal to the square root of I sub r square plus, well, I'm saying IC minus IL, right? Or I sub x squared. Let's just play with numbers now. Play with the numbers. I end up with square root of I sub r, which is 18 milli square, plus I sub x, which was 40 milli square. How much is that? What's 40 square plus 18 square equals square root of?
43.9.
43.9, right?
Yeah.
43.9
Milli.
K, or milli rather.
Yeah,
amps.
okay. Hard circuit.
Right. 43.9 milliamps. So, not a big thing. It's almost like an impedance in series circuit. Remember RLC series circuit? We had X sub C, we had X sub L, then we had X sub T. We found Z. Well, this is similar. Parallel. The current is is a dominating force here. So that's why I like to talk about current first. And I'm doing that now. When it comes to voltage, we know that voltage is going to be the same. So voltage total is equal to voltage across R, voltage across C, voltage across L. Voltage is all the same. That is the case there. And finally, so let's find out theta and Z. Z is equal to the square root of, I'm sorry, I can just say V over IT. This will work. In our case, it's going to be 180 over I total, which was 43.9 milli. Right?
Right? 80.
How much is that? What's 180 divided by 43.9?
4.1 K.
41.
4.1 K ohms. Now let's find the theta as well here. Theta is equal to the arc tangent. I sub t, I'm sorry, I sub x over I sub r. Opposite over adjacent. Okay, so someone with a calculator, how much is that? I sub x is
2 degrees.
how much?
I'm getting 2 degrees.
2?
2.
No.
I sub x over I sub r.
Yeah.
I sub x 40 milli.
Arc tangent of 2,
Okay, my bad.
2.2.
2.2, right?
Yeah, 2.2 arc tangent.
Oh yeah, my
which would
bad.
come to
Yeah.
65.8.
65.8 degree.
Yeah.
Yeah.
Okay.
You had intention.
Yeah.
I mean, I
That's
could have
close.
put that in there, just for the heck of it, I could have put that in there to see this angle of 0 degree, and this is now the angle of 65.8 degree. So Z comes up to be
Minus 65.
Negative 65.8.
negative 65.8 degree. That's the answer for Z. And it's set. Okay, so that's R, L, C, parallel circuit. Sweet, isn't it?
Sweet. Pretty much almost just like the other one.
Almost like the other one, right?
Except with this
Just
one you
the
work
one-
more with current.
Yes, and then also, some things are switched or swapped. I mean, if it goes a positive, it goes negative. In cases of current versus impedance or reactance. So those are the things you have to keep your head straight. But again, you know, most of these tests are going to be open book.
What else,
So you can take a look at those, yes.
What does the X stand for?
X is the reactance portion of the circuit. I mean, I have this as reactance, right?
Yes.
And this is reactance here. So when I add these two together, what should I call it? I can't call it IT. I can't call it IL. I can't call it IC. I have to call it another name. That's why I said IX.
Okay.
IX is simply the vector sum of the reactance current.
Alright.
Just like when it comes to X of t. X of t was when you had X of L minus X of C. But we don't know what to call that. We couldn't call it impedance, we couldn't call it resistance, we couldn't call capacitive reactance. We're going to call it total reactance. The total reactance, we had no name for it, so that's why we call it X.
X.
So now we'll call it the
Alright.
X of t. Anyway, that's all I have for now. So, do you want to close that?